G'day folks, and this is the pre-lecture snapshot video that leads us into quiz number 4, which is of course covering topics from weeks 9 and 10 of the semester. The topic's chemical equilibria, and we're going to be talking a bit about chemical equilibrium reactions, and these can all be described by a mathematical constant. So we'll have a look at some of these labels and some of the different kinds of equilibria you might see. We'll distinguish between two similar but slightly different ideas, molarity and molality, two different ways of measuring concentration. We'll talk about this idea of the reaction quotient, which is given the label Q, and then we'll move on to a discussion of Le Chatelier's principle, which looks at ways that you can shift these chemical equilibria around by changing things such as the concentration of the reactants and products, changing the pressure, changing the temperature. And we'll finish off by just making a few points about catalysts and how catalysts affect equilibria. So what is a chemical equilibrium? Normally we represent chemical reactions by saying that the reactants progress through some sort of chemical reaction to produce the products. And we usually write these chemical equations out with an arrow that points from left to right. But not all chemical reactions completely convert all of the reactants into products. In this case, we can say that the chemical reaction is in equilibrium, and the reaction is better represented with the arrows seen below, where there are still some reactants and some products, and they're constantly and dynamically interconverting between the two. And that's an important point. Chemical equilibria are not stationary, they're very dynamic. The reaction is moving both forward and backward. The point is, the forward reaction rate at equilibrium equals the backward reaction rate. And so the concentration of your reactants and products stops changing. In general, for any reaction at equilibrium, we can talk about the equilibrium constant, and it can be approximated as follows. If we have some general reaction between A and B, giving products C and D, you can see that these concentrations can be rearranged into a mathematical equation. Kc equals, and you can see the concentration terms for the products on top, and the concentration terms for the reactants on the bottom. These are also to the power of those stoichiometric coefficients at the front, which here are shown by lowercase a, b, c and d. And there are all sorts of equilibrium situations, and we have different constants to correspond to these. Kc is the general equilibrium constant. Sometimes you'll just see this one written as K. K with a P represents the equilibrium constant in terms of pressure, which is of course used for situations for gas phase reactions and so on. Ka is also known as the acid dissociation constant and is used for situations where you're generating some sort of concentration of H3O+, the hydronium ion. Kb is the corollary to this, where you're dealing with a basic concentration. Of course, all reactions always have, or all aqueous reactions always have some concentration of H3O+ and OH-, but they're usually either more acidic or more basic, and we use one of these two constants depending on that situation. In fact, if we multiply H3O+ concentration by OH-, we get the value for Kw. Ksp is the solubility product constant. It's used when we have sparingly soluble salts. And K-stability is one we'll talk about a little bit towards the end of this topic. We also introduce another term, and that's Q, the reaction quotient. It defines the extent and the direction of a reaction at any time before or after the equilibrium has been reached. You can see that the general expression for Q looks very similar to the way that we calculate K. But in this case, Q is used at any time, even when we're not at equilibrium. In fact, more to the point, Q is used to determine whether or not we are at equilibrium, and whether or not Q is greater than or less than K can actually tell us whether or not the reaction is going to move from left to right or from right to left. As the reaction proceeds, the value of Q changes, and eventually we tend towards equilibrium. And at that point, Q is equal to K. A really quick point to talk about a couple of ways of measuring concentration. The one that you're most familiar with, no doubt, is molarity, where a 1 molar aqueous solution contains 1 mole of solute in 1000 mils of solution, or 1 litre. In other words, moles per litre. Molality is a similar idea, and for aqueous solutions, 1 molar solution is equal to 1 mole solution. But as soon as your solvent has a different density, suddenly this relationship is no longer equal. A 1 mole solution contains 1 mole of solute in 1,000 grams of solvent. And the reason why you might actually use molality instead of molarity is it's not temperature dependent. These concentration units assume there are no interactions between solute and solvent species. But actually, there are a range of intermolecular forces, and introduces the idea of activity. We won't talk about that in detail now, but we'll talk about that much more during lectures. Le Chatelier's principle is an idea that we can use to rationalise how chemical equilibria respond to change. It's often expressed in all sorts of different ways depending on which textbook you're reading. Perhaps one of the more common ones might sound something like, a system in equilibrium subjected to a change will react so as to counteract the change. In other words, the position of the equilibrium can be changed by altering things like the concentration of reactants or products, the pressure of a gas phase situation, or the temperature. For example, when a reactant is added to a mixture at equilibrium, the reaction tends to form products. In other words, the equilibrium position shifts to the right. You can see in this scenario here where lead and iodide ions precipitate to give lead iodide. If you add additional lead ions or you add iodide ions to the solution, these are reactants, it'll tend to move across to the right-hand side. Conversely, when a product is added to the mixture at equilibrium, the reaction tends to form reactants. In other words, the equilibrium position shifts to the left, such as in this example here. What about for gas phase situations? Manipulating the pressure can also change the equilibrium position. This mostly concerns gases. Liquids and solids experience minimal compression, so it doesn't really apply to them in the same way. But as a general rule, an increase in external pressure is compensated by a reduction in the number of moles of gas, and vice versa. You've studied the ideal gas equation, and you know that the number of moles of gas corresponds to a particular volume. And so if we increase the external pressure, it will tend to try and minimize that pressure, and therefore move to the side of the equation which has the smaller number of moles of gas. Changing the temperature actually alters the value of the equilibrium constant. Raising the temperature of an exothermic reaction favours the formation of reactants. In other words, the equilibrium will move across to the left. Raising the temperature of an endothermic reaction will favour formation of the products. Finally, what happens when we add catalysts to chemical equilibria? A catalyst provides an alternative pathway for a chemical reaction. As you can see in this thermodynamic depiction of the reaction, we have an exothermic reaction. In this case, we can see in the image that the energy of the reactants is higher than the energy of the product, so we know it's exothermic. We also know to get from our reactants to products, we have to go over the activation energy. The addition of a catalyst actually lowers that activation energy. It's, if you like, it's easier for the reactants to get over that barrier and move towards being the products. The addition of a catalyst has more of a kinetic effect rather than a thermodynamic though. The catalyst only shortens the time needed for the reaction to reach equilibrium. It does not affect the equilibrium itself. So, for example, it can increase the rate of the equilibrium, but it won't change the overall yield. It doesn't change the equilibrium constant. So you won't expect those reactant and product concentrations to change. Just the rate of the reaction will change. It's an important point not to get confused by. Catalysts don't increase the amount of kinetic energy of the reactants. It just lowers the activation energy. So all of the answers to the pre-lecture quiz number 4 are covered in the video you just viewed. Go to the Moodle page, click on the pre-lecture quiz number 4 link and attempt the online quiz. You only get one attempt, but it's untimed. Good luck, hopefully you can get 10 out of 10.